Today's topic, eccentrically loaded bolted joints. Let's go. All right, we're going to do an example. So we're going to do our pre-example or pre-question ritual. Take a deep breath. Slowly read the question. A steel bar is bolted to a vertical steel beam with 4 by M20 10.9 bolts. A 20 kilonewton vertical load is applied as shown. Determine the governing fastener and its induced shear stress. Okay, we're going to immediately write down what we're solving for and the units. So a shear stress, tau, measured in megapascals. Alright, so one of the ways to be successful on this exam is to learn how to identify questions, different types of questions quickly. So we know that we're asked for a stress. So one of the tricks I like to use is we're going to quickly write down all the different types of stress that we can think of, and we're going to try to eliminate them so that we want to know if we're in a combined stress scenario, are we going to need to be combining stresses as we solve for them, stuff like that. Let's take a look at the different types. Axial stress. Do we have any axial stress here? Well, we're not given any preload information, so we're probably not in a bolt tensile stress problem. We're not given, for bending, we're not given any information about the steel beam or the column that it's bolted to as far as geometry goes, so we don't have an I value, so we probably can't do an MC over I type equation, so no bending. No axial, no bending. Shear stress. Well, it's pretty obvious by inspection that we've got a load that is perpendicular to the axis of the bolt. So we probably have some type of shear stress. Torsional. Do we have torsional shear stress? Again, probably. We're most likely going to get some type of rotation here. This is applying a moment to this connection, so we probably have some type of torsion going on. We're going to say yes on that. Transverse shear stress. We're not in a bending scenario, so no induced transverse shear stress there. And then I've got bearing stress in parentheses. It's a form of axial stress, but it's worth thinking about with a fastener or a rivet or something like that. Again, we're not given any material designations for or geometric information about the steel column or the bar or the beam or anything like that. So we're probably not in a shear tear out type environment, type situation, or like a fastener crushing or anything like that. So we're just going to go ahead and say no. Another thing to think of quickly, this diagram, and look, we haven't even talked about the values yet, but this diagram looks very, very similar to the diagram given in the reference manual for eccentrically loaded bolted joints. So that's another factor that's going to help us realize, okay, we have a good idea of what this problem is going to be. And last, this key phrase here, governing fastener, is given to us. That's a dead giveaway. We're going to be working with an eccentrically loaded bolted joint using the critical fastener method. Okay. This is good. Once we know we're using the critical fastener method, we have a procedure for how to do this problem, and it's fairly straightforward. It's not that hard. So let's go through that procedure, and I'll show you exactly how to do this and how really it's not that hard and we can do it quickly. Okay. If we're using the critical fastener method, we know we're going to be solving for the shear stress in the critical fastener. And that's very simple. It's our generic shear formula, but our total shear force over the shear area of the bolt. That's simply V over A. And Ft is going to be a vector sum of our primary shear stress and our secondary shear stress. And that's it. That's the only formula that's non-standard about how to solve this problem. So let's go through the steps. Step 1. we're going to find the bolt group centroid. By observation, we can see it's symmetric. That's good for us. So our values for the location, easy. 130 divided by 2 is 65, 140 millimeters divided by 2, 70. So we can see that that's symmetric. That's a critical component for how we're going to solve this problem. Our formulas are much more simple when we know the bolt group is symmetric. Okay, step 2. We're going to draw our force vectors. Okay, so we know we're looking for a primary shear. I'm going to put that in blue, and a secondary shear. I'm going to do that in red. Primary shear is simply the applied load divided equally between each of the 4 bolts. So I'm going to draw that just like this in blue. And notice for convenience, I've just labeled each of the 4 bolts A, B, C, and D, and I've drawn our centroid here. Now, primary shear acts in the same direction as the applied load. So, if you can imagine our 20 kilonewton load out here, each of these loads is going to act in the exact same direction. Okay, secondary shear is evenly distributed between bolts only if the bolt group is symmetric. We're symmetric, so we're good here. And in which direction does it act? Well, we've got a radius from the bolt group centroid to a bolt. The load acts at a right angle, perpendicularly to the radius, in the same direction of rotation from the applied load. Okay, great. Now, I'll just go ahead and finish all of these here. These are not perfectly drawn here, but I'm illustrating for you. You get the picture. Okay, let's redraw them in a way that's a little easier to analyze. And as we do this over and over again, you're going to get very quick at this. Instead of drawing the loads applied directly at the bolt, I'm going to draw them in a combined vector type of way. Excuse me, that one's wrong. Whoops. That acts in that direction. That direction. This one acts like this. This one acts like this. And now we're going to draw the resultant vectors. You might be asking yourself, why are we doing this? I think the answer becomes obvious as you draw the resultants. Probably should use a different color other than red, but that's okay. So we can immediately see that the resultant vectors for bolts B and D are noticeably longer and greater magnitude than for A and C. So we know that we've got either B or D as our critical fastener. For the sake of this problem, we're just going to choose D as our critical fastener. All right, good. Now, step 3, we are going to compute the primary and secondary shear forces. Now, again, this is the only formula that we really need to know for how to solve this problem. Let's do primary first, again, because it's the simplest. Your primary shear force, F prime, is the applied shear force over the number of fasteners. So N number of bolts. Let's quickly solve for that. 20 kilonewtons F prime equals our 20 kilonewton applied force divided by 4. F prime is 5 kilonewtons. Simple. All right. F double prime, a little bit more complicated. We know we're symmetric, our bolt group symmetric, so we've got our applied load times the eccentricity of the load to the centroid of the bolt group. So we'll write E as eccentricity divided by the number of bolts times the radius from the bolt group centroid to the critical fastener. So let's quickly compute E. To do that, let's take a look at our diagram here. All right. What is our eccentricity of the load? It is this distance. And guys, on any example like this, if it's a quantitative problem, it will have all the dimensions. It shouldn't be very hard to find. So I know it's going to be, I'll just quickly rewrite it here. E is going to be 200 millimeters there, plus 30 millimeters, which is this distance here, plus 70 millimeters. E is equal to 300 millimeters. So we'll get this out of the way. Keep working. Oops, 300 millimeters. Great. Now, N, we know N is going to be 4. What is R? Okay, well, we haven't solved for R yet, even though we've drawn out the bolt group centroid. Let's quickly solve for R. We know that this is 140, this is 130 millimeters. Let's solve for R here. Now, that's going to be applicable here, here, here. Doesn't matter which triangle you choose. 65, 70 millimeters. R is easily found to be 95.5 millimeters. So let's go ahead and plug in here. F double prime equals 20 kilonewtons times 300 millimeters eccentricity divided by 4 bolts times 95.5 millimeters. That computes to 15.7 kilonewtons F double prime. So we've got 2 values here. Okay, now let's look again at our vectors. We know that the total shear force is a vector sum. Well, let's look at our vectors. It's going to be hard to sum these. I don't even want to attempt it. What we're going to do to make this simpler is we're going to break our secondary shear force into X and Y components. Once we compute what these are, then we can do a vector sum, and that'll be a lot easier. So, how are we going to find that? Well, we need to do a little bit of trigonometry. Not a huge deal, but it's going to take us a moment. So, let's zoom in here, our critical fastener, and let's draw this triangle a little bit bigger. Do it just like this. Centroid, fastener, 70 millimeters, 65 millimeters. Shouldn't leave my units off. That's our R. This is our vector. It's acting at a right angle. That means we have a new triangle of 70 millimeters, 65 millimeters. So we need to do, what is this angle here? We'll call that theta. Inverse tan of theta, theta equals inverse tan. 70 over 65, theta equals 47.1 degrees. Okay, let's take another look at this triangle here, and let's try and solve for its X and Y components. We know that our vector here is 15.7 kilonewtons, angle 47.1 degrees. What's our y value? What's our x value? Easy. Trigonometry, we can do it. Y value, 15.7 times the sine, 47.1 degrees. It's going to equal 11.5 kilonewtons. Our x is going to equal 15.7 cosine, 47.1 degrees. X component is going to equal 10.7 kilonewtons. You can see I've cheated a little bit. I've gone ahead and just written it out for us. Now we can find that value. Excuse me. So, Ft originally is this formula, but we're going to rewrite this in x and y components. It's going to look like this. Sum of all of our x components squared, sum by the way. Oh, the sum, there you go, sum of our y components squared. This is what we're solving for. We can now solve that. That's easy. 10.7 kilonewtons squared plus 5 kilonewtons plus 11.5 kilonewtons squared. Turns out that our Ft total equals 19.7 kilonewtons. All right, so what did we find here? This is the resultant shear force applied to our critical fastener D. Really, it's going to end up drawing like that, 19.7 kilonewtons. Maybe I should redraw it here. 19.7 kilonewtons. That's the maximum shear force applied to this bolt. That's the hardest part. One more step and we're done. Last step, step 5, compute the bolt's shear stress. This is very straightforward. The shear stress tau in our critical fastener is equal to the resultant shear force over the shear area. Now, a couple notes here. The reference manual does not give minor diameter information for metric bolts. We saw from our problem that they're M20 times 10.9 or by 10.9 grade bolts. We're going to just go ahead and assume that that's nominal diameter. All right. So let's let's go ahead and solve this. This is pretty straightforward. 19.7 kilonewtons is our applied force, or our resultant force, times the bolt area. Okay, let's pause real quick. If we're not paying attention, we can screw up units here. And there's no sense missing a problem on this exam for units. So I'm going to do some steps that look maybe a little goofy from a unit standpoint, but this is just how I do it, and I don't want to make any mistakes on units, so I'm going to go slow. I'm going to go ahead and convert from kilonewtons to newtons, and I'm going to convert from millimeters to meters, so that I end up with Newton meters. Excuse me, newtons per meter squared, which would be pascals, and I'll then reconvert it into megapascals. So 20 is going to become 20. That's going to go 1, 2, 3. Excuse me, other way around. Sorry. 20 millimeters goes 1, 2, 3. All right. Forgive me on that one. You're going to end up with 62.7 megapascals. That's it, guys. That's easy. So, back to the original question. Which fastener was our critical one? Simple, this guy. And what is the applied, or the induced shear stress there? 62.7 megapascals. Now notice, we didn't have to spend a whole lot of time on this diagram. Excuse me. We didn't have to spend a whole lot of time on the diagram. There was Not a whole lot of information given here, nothing really erroneous that could throw us off, but we didn't have to spend a lot of time looking at this. We really only needed our E value and our 20 kilonewtons. So, things to take away. Always go slow in writing units. There's no sense in missing a problem here, just for units. The eccentrically loaded bolt info in the reference manual is very difficult to use. The formulas are confusing. There's nothing near as simple as this formula. There's all kinds of sums and all kind of mess given in there, and it's just very confusing. If you haven't done this type of problem over and over and over again and learned to recognize just by observation, this is the process I'm going to use, you're never going to solve a problem like this in 6 minutes. If you're going to try to decipher the formulas given in the reference manual, it's toast. And then lastly, you might be wondering, why did we spend all this time drawing vectors? To me, it makes sense that these first several steps here were totally qualitative. We didn't do any math. We quickly identified a critical fastener. It didn't take us long at all. If you're given a big bolt group and you don't know what you're looking at, you've never seen it before, maybe it's going to be hard for you to find the critical fastener. Draw the vectors. You won't go wrong. That's the simplest way to do it, in my opinion. Now remember, you don't have to be a genius to pass this exam. You can do it. Thanks for watching.